So this example we explained in class is about the static friction as the centripetal force. So static friction plays the role of the centripetal force. So let's look at this this example. It is a normal force as provided as a centripetal force. So the question is talking about there is a banked road, a circular path. When the car is traveling along this circular path, it has a radius of r, so the c is the center. And then if you look closer and take the front view, so we're going to have this graph. Center is here. The car has two forces acting on it. One is the gravity mg, and the other one is the normal force along this way, perpendicular to the slope. Then we resolve into the components. So before you do that, you need to decide the reference. So we always use one of the direction, which is the centripetal direction, as x-axis, and then the other perpendicular direction, which is the vertical here, is y direction. As we mentioned, there's another direction actually is pointing directly out of the screen. You can tell here, and basically just like go out from the screen is where the car is moving at this position. In that position, we don't need to worry about too much. Most of the cases, that's not a concern. Look at these two directions, centripetal and vertical. Resolve the force, the only force is not on the either of the axis. So we resolve into x component and becomes Fn sine theta. So angle theta is equal to the banked angle. And then Fn cos theta is on the y component. Now you can see, if you look at the x direction, there's only one force, which is a component of the normal force. And then, of course, that's the only net force centripetal, so it should equal m mass times the acceleration, which is the centripetal acceleration using the formula v squared over r. On the other direction, the normal force component on the y, Fn cos theta, should balance with mg, because along the y direction there's no acceleration. So if they're equal, we create another equation. So now to solve this for the v, you can do a lot of different ways. You can solve the n here, plug in here, or you can just simply divide the two equations. So that's always a technique you can think about using. Because if you divided the two equations, so you're creating another equation which still should be equal on both sides. And then as a result, you can cancel the Fn, and you leave sine theta over cos theta. On the right side, if you divide it, you can see the m is a common factor, will be cancelled out. And here you just need to simplify. You should get v squared over rg here. And finally, the sine theta over cos theta, you can look at it here. They can be simplified into the tangent theta. What you can do is just write a sine theta as opposite of hypotenuse, cos theta as adjacent side of hypotenuse. Then you can multiply hypotenuse on both numerator and denominator. You can cancel both of them. Then you get an opposite of adjacent side. So that exactly should be the definition of tangent theta. Okay, if this is tangent theta, multiply the g r over the other side and then take square root, you should be able to find out the velocity. So that is going to be the velocity that can travel along the banked road without relying on any friction.